modern cell membranes are really tough, they're stable, they're great barriers. They allow cells to control everything that gets in and out. But that requires a lot of fancy, highly evolved machinery, which wasn't around by definition for the first cells. So those membranes had to be really different.
But what might these primitive skins around cells have looked like? Jack found the inspiration in soap bubbles.
So these are delicate. They really illustrate the idea that there's an encapsulated space. That was pretty good.
Soap bubbles are made from molecules called fatty acids, primitive chemicals that Jack thinks were produced on the primeval Earth inside hydrothermal geysers.
The right kinds of minerals could catalyze the assembly of fatty acids from simple things like carbon monoxide, methane, water. One kind of nice way that that could happen is in a hydrothermal vent system, and then they could bubble up to the surface.
So Jack set about recreating the chemistry of a geyser in his lab, and eventually created fatty acids. Now, he mixes them into a primordial chemical soup made of water, salt, and amino acids. And he watches as a remarkable transformation takes place.
So membranes form in sheets, and they're kind of wavy, and the edges are kind of high energy. So what happens is they close up on themselves, and they make little round structures. So they're closed structures.
These little dots are actually hollow bubbles, less than 1,000 inches across. This is what the first living cells may have looked like 4 billion years ago. Jack may have recreated the seeds of life under his microscope. But it is impossible for life to evolve unless cells can pull off one crucial task. They must be able to grow and divide. This is how seeds blossom into flowers, how a caterpillar becomes a butterfly, and how a baby becomes an adult. Soap bubbles grow in the air nothing more than a puff of air. So, Jack slightly jiggles the vesicles and watches something incredible happen.
Membrane will start to grow spontaneously. What we see in the microscope is that it grows in a peculiar way. The whole initial vesicle turned into a long, flexible tube.
These fatty acid membranes are achieving one of evolution's most essential jobs, self-replication. They will do it automatically. To Jack, this is a sure sign he's getting close to understanding how the miracle of life began.
So in the cycle of growth and division, that's very much like primitive cell growth and division.
Jack may very well have found the recipe for life's earliest cell structure. But to be truly alive, genes are the molecular identity that can pass from a cell to its structure. With the double helix of DNA. It's the most complex chemical molecule we know, made up of tens of billions of atoms. DNA controls every detail of every living thing. The color of our eyes, the shape of the leaves on a tree, the way even the most simple bacterium swims. And every time a cell divides, it places a copy of its DNA in both cells of the new generation. At the University of Manchester in England, chemist John Sutherland is trying to discover how DNA came to be. The key to discovering how we came to be.
For me, the really interesting point here is the transition between chemistry and biology. It's always been assumed that you need to have an informational molecule. You can't really have life unless you can have inheritance, so you need to have something which you can inherit, the information.
version of it, a single-stranded informational molecule called ribonucleic acid, or RNA. Scientists studying the origin of life have long believed that RNA might be the precursor of DNA, a simple carrier of life's genetic code.
So the name of the game, if you like, is to make RNA from very, very simple precursor chemicals using simple organic chemistry under conditions which could have prevailed on the early Earth.
RNA is a giant molecular string made up of 4 different basic building blocks. The order in which these blocks are arranged forms a genetic code.
Well, when you look at RNA, you, as a chemist, you're in sort of astonishment, really, at just what a wonderful molecule it is. It's complex, it's a really beautiful structure, and you inevitably wonder how on earth did that structure arise? How on earth did chemistry produce it?
RNA's structure looks simple, but looks can deceive. Each building block is actually made of 2 parts, a sugar molecule and a nuclear base.
Chemists found they could make nuclear bases, and so when they then realized they could actually make the sugars, they just thought, we must be able to join them together. And so they tried for many years, but the problem was, chemically, you just can't join them together.
For years, scientists tried and failed to whip up some RNA by placing a sugar and a base in a pot and heating it up. But John realized that the primordial soup metaphor was too narrow. Early Earth's kitchen had more than just a stove top. It had an oven, a steamer, and a freezer.
It's sitting there for a while, and then the temperature goes up, and the pond starts to evaporate, and the residue that's left after the pond's evaporated is then heated for a period, and then it rains again. After it's rained, the sun comes out. So it's a sequence of events rather than one static set of conditions.
So John and his team recreate the sequence of wetting, drying, heating, and cooling that would have taken place on early Earth. And incredibly, for the first time, these chemists achieve what none before them ever did. They create 2 of the 4 basic building blocks of RNA.
Well, now we have to find a way to make the other 2, and I think we're pretty close to doing that. And then we want to string them together to make an RNA polymer molecule, and we've actually recently found some ways in which we think we can string them together.
John may be hot on the trail of the first genes, but there's no guarantee he will ever stumble upon the answer in a lab. Now, a few renegade scientists are taking another tack to the origin of life. They think the most primitive life forms might still be alive and lurk right under our feet. All the life we know today, even the simplest of microbes, shares the same biology. We're all from the same tree of life. But we know our incredibly complex biology could not have been the first form of life on Earth. What was life like before the life we know? Finding that life might help us understand how we got here. And the answer could be right under our noses.
All life so far studied is the same life. It's never been clear to me that you can't have one form of life on the planet at the same time. I think it's entirely likely that we share this planet with a genuinely alien type of life. Alien not because it necessarily came from space, but because it belongs to a different tree of life from you and me. Remarkably enough, it turns out that nobody has really thought to look for life on Earth as we don't know it.
Paul Davies is one of the world's leading cosmologists. He's the first to admit he's not a biologist, but he's not afraid to venture into their territory and ask questions no one else thought to ask.
We don't know how a mix of non-living chemicals turns itself into a living thing. We don't even know whether this is a very likely sequence of events or a very unlikely sequence of events. But let's suppose it's very likely. Then shouldn't it have happened many times over, right here on Earth?
Paul's term for possible homegrown alien life is the shadow biosphere, and he has a plan about how we might discover it.
We can